Okay, welcome back, everybody. And so today, actually, we have a lot to go through. So first, I would like to start from where we stopped last time to finish the analysis for the running time of the insertion sort algorithm. And then we're gonna compare it with another more efficient algorithm, which is merge sort. And by basically comparing their running time and to see how merge sort can basically outperform insertion sorts in a more general case. Okay, so let's pick up these equations first. So we, from the pseudocode, we hold the assumption that each line of code, right? If we got each line of code and if we run it for just once, it will cost us constant amount of time. Okay, so the total cost for that line of code is the one-time cost times the total number of times. Okay, so if the first line of the for loop has been executed for n times, and each execution costs C1, then the total cost for that line is C1 times n. And that is a straightforward multiplication. And all we need to do is to collect the cost for all those lines by summing up a bunch of products. That'll give us the total running time for the algorithm. And the total running time is denoted by the capital letter T. And these notation is something we will use throughout the whole course to indicate the running time of some algorithm. All right. So another thing, let's review again, is the notation Tj. Okay. So this is a variable. This is something unknown, right? And this superscript j is to say that this Tj is the cost for the Tj is the number of execution times for these while statements. Okay, for this line 5. So because in each iteration of the for loop, it has a different j value. Okay, and also the comparisons needs to be made between the key and all the elements before the key are also different. So this is a quite random process. So Tj is something we don't know. So we can simply use such a notation to make sure that we can carry out analysis. Okay. So after we denote this Tj, then we're able to express the summation using these complex mathematical expressions. Of course, we don't like the TJs and we want to get rid of it. Okay, and in next slide, we have covered this slide already, right? So we want to get rid of the TJs case by case. Okay, so in the best case, when the input is already a sorted sequence, then this while loop, the body of the while loop is not executed, right? Because the while loop will only execute if the element before key is greater than the key. But in this case, it's an ideal case. No element before the key is greater than the key because it's already in a sorted order. So the body of the while loop will be executed for 0 times. And the while this line 5 will be only executed for once for all j's. Okay, so that makes things much easier, and the complex Tn simplifies to this linear form. Okay, so it's a bunch of it's just this something we can simplify to a, these coefficients that we can simplify to a, and this bunch of coefficients we can simplify to b. So this running time of the algorithm, of the insertion sort algorithm, under the simplest case, in the best case, is a linear function. Okay, so if we draw a linear function, on the plane in the 2D space, then it increases steadily. So this is something very ideal. Okay. All right. So, but we cannot always have the best case for insertions for any sorting problems. So usually, the sort problem needs to deal with some very random input scenarios. So let me first stop share and let me play the slides. So from the next slide on, we're gonna talk about something new here. All right, let me share it again. Okay. All right, so now let's go to the opposite side. Let's go to another extreme situation where the input case is the worst case. So by worst case, we mean that the input sequence is in the reverse sorted order. Okay, it is totally opposite to what we are expecting. Okay, and that means all the so the biggest element is the first elements, and the smallest is in the last one. So in that worst case, what will happen in the while loop is that we found that we need to compare the key, which is AJ, with each element that is ahead of it, because all the elements are greater than AJ, right? Because the total sequence is in the reverse order. So that means we can also determine TJ, right? Because in the J's iteration, when we're looking at AJ, there's basically J comparisons we need to make, okay? So because this is the worst case and we need to make J comparisons for each possible value for each iteration of J. So that makes a TJ equals to J, okay? And then if we look at the summation expression and substitute this TJ equals J into our summation of TJ here, okay? It will give us a arithmetic series, right? If we add 2 plus 3 plus 4 until n, then this is a series. We can compute the summation of it, which is this expression, right? It's n times n plus 1 divided by 2 minus 1. And also, we have another expression, which is J minus 1, right? This is because in the previous slide, we have not just the summation of TJ, but also the summation of TJ minus 1. Okay, that is for each line of the body within the while loop. Okay, so yeah, given TJ equals J, then we can simplify, then we can substitute these two terms into the term for the total running time, the capital T. All right, and that makes things solvable in a slightly more complex form. And if we look really closely and we combine all the coefficients for n's with the same order, right? So this is a quadratic term, n to the power of 2. And this is a linear term, which just have n, and this is a constant term. Then we can have pretty much a quadratic function, okay? And if we use a and b and c to denote all the coefficients, then we can have a times n squared times b times n plus c. Okay, so yeah, in the worst case, we can conclude that the running time of the insert and sort is a quadratic function. Okay, it's already worse than a linear function, because whenever you draw a quadratic function, right, it goes, the curves go up, right, really quick as n grows larger, right? It's not a linear steady increase. All right, so anyway, this is expected because it's the worst case, right? It's totally the opposite, totally the reverse sorted order as inputs. So I see a question, in what case we want to know the best case running time or the worst case? And usually, I think the most common most common usage is the worst case, because we want to know what is the biggest possible cost, right? Knowing the best case doesn't cover all the practical scenarios. And as we will see in the next slide, actually, we want to see a more stable analysis, a stable estimation, which is the average case, okay? Slide showing the pseudocode. Why does TJ occur twice? Oh, yeah. So because the while loop has 2 lines within its body. So the while loop is from line 5 to line 7, okay? And the line 5 will be executed one more time than line 6 and line 7 in each iteration, okay? So in iteration J, then the line 5 will be executed for Tj times, and the body of the while loop will be executed for Tj minus 1 times, okay? So this is because in order to terminate the while loop, the loop counter needs to, the loop statement needs to be executed one more additional time than the bodies, okay? And there are 2 lines all within the while loop, so there are 2 Tj minus 1. Okay, so let me return to the worst case. So technically, we want to know the average case. That is, what is the most common input cases? We both know that we all know that both cases, neither case are most common, right? It's in practice, usually we get something somewhere between the worst case and the best case, okay? But the worst case can sometimes be useful for us to estimate what the most likely average case is. So for example, let's further look at the average case for the insertion sort, okay? So we usually focus on worst case because it gives an upper bound, and we want to know the upper bound for any input, right? So it will guarantee that the algorithm will not grow infinitely big, right? We kind of have a guarantee in our mind, right? And for most of the algorithms, the worst case failure occurs quite often, though we didn't know about that. There's randomness in the inputs, okay? So for example, like searching a database when there's no sufficient inputs information, or when the information is absent, right? Okay, so now let's look at the average case for insertion sorts. So here, this sentence says average case is often as bad as the worst case, okay? So this is bad news for us, and let's see why this is the case. So to a sorting problem, the average case means that we don't know about the inputs in sequence. This inputs sequence can be a very random sequence in totally random order, okay? So suppose that we have such a random input, okay? So now we need to estimate what Tj is given a random input. And the Tj is the number of comparisons that Aj needs to compare with all the elements ahead of it from A1 to Aj minus 1, okay? So to a real random number, a random sequence of numbers, we can assume that on average, half the elements before Aj is smaller than Aj, while the other half is greater, right? Because that is how we usually perceive the randomness in data, right? Only if it is a very random number, then we are likely to have half the number that is greater than Aj, and while the other half is smaller than. Okay, I think this assumption makes sense. So if we take this assumption, then we can estimate that Tj is almost half the size of J, half the value of J, right? Because roughly we can have, we need to make, we need to compare half of the elements ahead of the AJ, okay? So the resulting average case running time can be computed if we substitute this Tj equals J divided by 2 into the summation term, okay? So, and we will notice that because the summation looks like the one in the previous slide, it's like this term, right? The summation of J. It doesn't matter if it's J or half the J, right? If we let J equals J, substitute the J with J divided by 2, okay? It's still, the summation is still a quadratic function, only with smaller coefficients, right? There could be some coefficient like this divided by 4 or something like that. But this is still a quadratic function. And that means the form of the total running time will not be very different from this general form. It's still in the form of a times n squared times b times plus b times n plus c. Okay, so that's why we say even if it's a average case, then it makes sense to estimate the running time using a quadratic function. Okay, just like the worst case running time. All right. All right. So it basically shows that in certain sorts, grows the running time of uncertain sort grows as fast as a quadratic function. So now let's keep this in mind, and then we're gonna see another algorithm in order to compare it with the uncertain sort. Okay. So before that, let's look at the concept of the order of growth. And this is something that we're gonna formally introduce in next week's course, but in next week's class. But now let's have some brief idea of what it is about. Okay, so it means we can simplify. We can use simplified abstractions to analyze uncertain sorts. Okay, so we can ignore the actual cost, but use constants instead, and we can use the abstract in such a form, T of n equals this generic quadratic function, okay? So a further simplified abstraction is that we only care about the order of the growth, okay? So we can consider the highest order term here, right? We can only consider highest order term, and we can kind of ignore the lower order terms, because compared to the function a times n squared, the lower order term is relatively insignificant as long as your input n is big enough. So the difference can be smaller when n is small, okay? But to algorithm analysis, we should consider extreme cases, like usually the input can be very big, and usually the algorithm can be run for a lot of times, so the input size is quite big. Okay, so we can ignore the not just the lower order terms, but also ignore the coefficients like the a's. Okay, because it's a constant. It can be different from different machines, from different hardwares, but it doesn't affect the nature of the function. So we just need to use the most essential fact, which is that the running time is expressed by a quadratic function. So we should keep this core term here, n squared, n to the power 2. That basically indicates that the running time of uncertain sort runs as fast as a simple quadratic function. Okay, so this is what we mean by analyze the order of a growth for a function. Okay, so this big theta, this Greek letter big theta notation is something that we're gonna formally introduce in the next class. Okay, but here we just as a preparation, we just need to, let's have a rough sense of how the notation is used. So this big theta wrapped around n squared means that our function grows almost as fast as a quadratic function. And from our common sense, that a quadratic function always grows slower than the cubic function, right? Then n to the power 3. If we compare these two functions, then the n to the power 3 grows much slower. It has a much steep slope. Okay. So that's something, a piece of brief information about order of growth. All right. Now let's look at an alternative approach to the sorting problems. Okay, so this is the first time that we introduce the term divide and conquer here. So it's basically an approach. We'll see this approach a lot in this course. Okay, so it's basically an approach that, given the problem, we can break the problem into smaller problems, and we call these smaller problems subproblems. Okay, and those subproblems, they are similar to the original problems, but are only smaller in size. Okay, but they are in nature the same type of problems. Okay, and then after the division, we can solve the subproblems recursively by calling the procedure defined here recursively. And after the subproblems are solved, what we need to do is to simply combine the solutions into a solution to the original problem, right? I think the idea is quite straightforward. We need to do several steps, like divide and then solve recursively and then combine all the solutions. Okay, so here recursive is a key term. So we basically, in this type of divide and conquer approach of solving problems, we need to write some recursive algorithms. Okay, so in a recursive style of algorithms, we need to call the function being defined. Okay, we need to call themselves recursively for one or many times. Okay, so there are three steps involved. First is called divide. So we need to divide the problem into a number of subproblems, right? And conquer. So this conquer step is basically to solve them recursively, okay? And by that, if the subproblems can be divided further, then we will go deeper, right? Until we reach the smallest subproblem, okay? So if the subproblem can be divided, we need to divide them recursively again. If the subproblems is the basic case, it can no longer be divided, then we just solve it in a straightforward manner. Okay, and the third step is called combine. It is how we collect all the solutions to all the subproblems resulting from the dividing step in order to have the solution to the original problem. Okay, so we will have a complete chapter about the divide and conquer approach, which we will introduce hopefully in the next week on Thursday's class, okay? But this you can think of it as a warm-up for getting into the idea of divide and conquer. All right, so the merge sort algorithm we're gonna introduce here belongs to this family of divide and conquer algorithms. All right, and we will know that the worst case running time is much less than in search and sort. All right, let's look at the ideas. It's quite straightforward. Okay, we simply need to divide the input sequence into two subsequences of almost equal length, because we divide it into the middle of it. Okay, and we make sure that the first half and the second half, they all contain half the number of elements in each. And then we just sort the two subsequences recursively using the merge sort algorithm. And the third step, we merge the two sorted subsequence to produce the sorted answer. Okay, and because it's a recursive algorithm, and in order to terminate a recursive algorithm, we need to have the boundary case or the bottom case defined. So what is the bottom case for merge sort? Given a input, so let's imagine that in our mind, given the inputs that has only two elements, say two numbers, 5 and 6, right? If we want to sort 5 and 6, then we can still split it, right? 5 and 6, we can split into two subsequences. The first one has only one element. So for the merge sorts, the basic case is the length of input, the input of length 1, right? Because given the sequence that only has one element, then we don't need to do anything, right? But for inputs that has two numbers, we still need to compare the two numbers, right? We need to first divide it, and then into two subsequences, and then call the algorithm again. Okay, so keep in mind that the basic case, the bottom case, is input of length 1, and that is where we don't need to do any divide anymore. Okay. All right. So actually, the key step is the merging step. It is the combine step, right? Because if we take that example again, we have 5 and 6, and we put 5 in the first half and 6 in the second half. Then how do we merge the result so that the solution is a sorted one, right? We need to make kind of comparison between 5 and 6, right? And take the smaller one out, right? So the key is really at where merging step is, how merging step is implemented. Okay, so let's look at this implementation for this merging step. All right, and this procedure, is something we implement using the pseudocode, and it accomplished the merge step. Okay, and its function is to take two sorted subsequences and produce a sorted answer. So if we look at the arguments, let's go to the next slide. If we look at the arguments, okay, so it has 4 arguments. It needs to take 4 arguments as inputs. The first one is the array, where we store all the elements, where we store the input sequence. And the last 3 arguments, P and QR, PQR, they are integer numbers. Okay, they are the indices, okay, and they follow these constraints. So P is the leftmost, is the smallest, R is the biggest, and Q is somewhere in between. Okay, if we plot them in a line, it will be like this. P is the smallest. Okay, so these 3 indices actually define 2 subsequences. All right, that is from P to Q and from Q plus 1 to R, okay? And these correspond to the 2 subsequences that are already in sorted order, okay? This is also important. The condition is also important. We assume that the sub-arrays are already in sorted order, because we are talking about the combine step. The combine step is the 3rd step after all the sub-problems are already solved, right? So what this procedure does is to merge these 2 segments to replace the current sub-array from P to R, okay? So it is a kind of an in-place algorithm. It doesn't return, it doesn't allocate something, doesn't allocate new spaces. It only, actually it does, but there's no new array returns. So the elements within A will be changed so that it reflects the merging result. Let's look at the code in the next slide. Okay, so okay, I have one more additional slide here to help you think about the procedure. So you can actually use a card playing analogy again. So imagine that there are two sorted piles as inputs. And you know that the smallest card is on top. So our job is to merge these two piles. And the resulting pile will be a sorted order. So what we need to do is that we can choose the smaller, we can like take two cards from each pile, take one card from each pile out and compare the two cards on top of the two input piles. And then we always choose the smaller one and to place it on the output pile, right? And we will keep doing this until one pile is totally empty, until we consumed all the cards in one pile, and then we just append the remaining pile to the end of the output pile, right? I think that procedure is quite, imaginable, right? You can think of two piles in front of you and you just compare the top elements. A two variable for loop. Actually, yeah, once we look at the, let's look at the pseudocode and you will find that actually there's just a one variable involved here, okay? The implementation of this within this pseudocode is quite interesting, as it's allocated some new spaces in memory, okay? But there's only one variable in the loop, okay? So here, these two statements says that because each basic step takes constant time. So what is a basic step? We just take one card out of each pile and compare their value, right? It's just a simple comparison. And that simple comparison doesn't cost a significant amount of time. It's just a comparison. So it's a primitive step, right? So we just think of that this basic step takes constant time. And we need to compare at most n basic steps. So we can think about that, the merge, we consider the fact that the merge only takes big theta of n times, which is a linear function. But we will come back to this point later, okay? I just show the conclusion a bit ahead of time here. All right, let's look at the implementation now, okay? All right, 17 lines of code, okay? But no worry too much. A lot of the codes are just for the purpose of initialization, okay? All right, line 1, it computes something called N1. N1 is to use Q minus P plus 1. That is the length of the subarray from AP to AQ. Line 2 computes N2, which is the length of the second half from AQ plus 1 to AR. Right, use another color, right? And in line 3, it creates two new arrays to store the two subarrays, okay? It uses some additional memory space to copy the elements to those new spaces, to L and R, okay? And you can notice that the length for these two arrays, they are N1 plus 1 and N2 plus 1. So there's one more element than needed. So we will see why this is the case. All right, so next, from line 4 to line 5, it's two set of for loops, okay? They are not nested, they are not embedded into each other, but they are two standalone for loops. The first for loop is to copy the elements from the first half of A to L. And the second is to copy the second half to R, okay? And from line 8 to line 9, there's some special operation that sets the last elements of L and R to be infinity. Okay, so these infinity are the biggest numbers in the computer system. So it is larger than any number it's compared with. So we'll see why these, how these sentinel values, so it's called sentinel values, infinity, will be useful. Okay, it basically makes it easier to implement the algorithm in the next few steps. All right. So actually, the merge steps happens after line 9, because before line 9, everything is about initialization. Okay, is to lay out, is to allocate the memory spaces and to get ready for the merge steps. So we now focus on the merge step. So it will basically perform that many basic steps of comparison and copy. Okay, the for loop counter is K. K will iterate from P to R. It basically iterates through all the elements in the input array. Okay. Now let's look at further into this comparison and copy code. Okay, from line 10 to line 7 here. If we use example, it'll be much easier to show how this code works. Okay. Within each step of the for loop, there's a if-else branch, right? It's just two conditions. And if we look at the condition of the if, it's Li is less than or equal to Rj. So it picks the smaller one, right? So if Li is smaller than Rj, then Li is copied back to Ak, and I will increment by 1. That is just like when we compare the two cards on top of two piles. If the left pile has a smaller card, then we take that card out and put it into the output. That is exactly why this code is implemented. Okay, so from A to B, if we make the comparison using the example inputs, we'll see that the first two elements being compared is the number 2 here and the number 1 here. And since the number 1 is smaller, so the 1 will be copied to AK, which is here, okay? And then the J is incremented. So in the next iteration, these two numbers will be compared, all right? After comparison, so we'll take the L elements back to the A, and the K is also incremented, and the I is incremented. Okay, so this is a very clear demonstration of how the algorithm runs for these merge sort steps. Okay, so as we see that the element, the array R will hit the end first. Okay, but since there is a sentinel element at the end, the comparison will be can be, even if after R is empty, the last element can be compared with the remaining elements in L, and the 7 is smaller than the infinity, then it will, the 7 will be copied to the last position of A. Okay, so after this step is done, we see that A is sorted. So clean and nice. And it basically shows how merge occurs, right? The code is compact and easy to read. And the only parts that is a little bit tricky is the sentinel parts. But in the, we'll see that this is not necessary. We don't necessarily need to implement this But with some additional code, we can implement the merge step without using the Sentinel symbols. And that is one of the questions in the first assignments, okay? Which is to ask you to implement the merge algorithm without using the Sentinel elements, but it will let you use some additional variables. All right. That's just, we're just halfway done in merge sort because we just implemented a merge algorithm and the merge procedure. And merge is just the final step, right? The assumption is that we are already given two subsequences that are already sorted. And only based on this assumption, the merge will do, will give us the valid output, right? So we will need to look at how the implementation of merge sorts, final implementation looks like, okay? So let's skip this one because the loop invariant is to check the correctness of algorithms. This is now optional content for this course. And let's directly go to the running time. And we already have the conclusion in several slides ago, which says the merge procedure runs within linear running time, right? So it's easier to understand. It's very easy to understand because if you look at the code, there's a for loop that iterates from the first element of A to the last element. So it's just n elements in the sequence being merged, right? And if we look at all these lines, line 1 to line 3 takes constant time. Line 8 to 11 also constant time. And there are two for loops from line 4 to line 7, which takes that many of time because it's a linear structure. We just go through all elements once. And from line 12 to line 17, it's also a linear. Also takes n iterations. So altogether, I think this is a typo. It shouldn't be constant time. It should be big theta of n. So if we consider two parts of big theta of n, in total, they should take big theta of n time. Right? That's a very straight conclusion. Right? So now, given the merge algorithms, we can use it as a subroutine to implement the merge sort procedure. Right? Finally, we want to implement the merge sort. And if we look at the code, it's actually quite simple. That's it, just 5 liners of code. So given the inputs elements A, the inputs array A, the starting index P, and the index R, it means that we want to sort the elements within this sub-array, okay, within the sub-array of from P to R. So what this algorithm does is that we will check whether P is smaller than R, okay? If they have equal values, then that means there's only one element in the sequence. Then we don't need to do anything at all because there's no need to sort a one element sequence, okay? So otherwise, that means there's space for division, okay? Then we can divide A into 2 sub-arrays. So now we have the floor notation used, okay? Because it's not always even numbers of elements in the sequence. We will take the first half from P to Q, right? That contains the first half of the elements. And the second half from PQ plus 1 to R, it contains the second half of the elements, okay? And we'll have some recursive calls on each sub-array. We'll have the recursive call on the first half from P to Q, okay? Notice that the ending index is Q. And a second recursive call from cube plus 1 to R. Notice that here, this is a different starting index. And lastly, after these two merge sort recursive calls are done, we need to call the merge procedure, which is defined in the previous slides previously. Okay. All right. So because this is a recursive algorithm, I think it'll be easier if we use a simple example to look at it. Okay. Oh yeah, by the way, the input is a general, it is very general form because we need to provide we need to provide not just the input array and also the starting index and the ending index. So in the case of an entire sequence, if we want to sort it, we can just call merge sort from 1 to n or from 1 to a dot length. Yeah.
Good question.
Yeah.
So wouldn't line number 5 wouldn't be return merge?
We don't need to return merge. The merge is an inline operation. So it changes the elements in A directly. You see, in the merge.
Oh, I got it.
Yeah, the AKs are changed directly in memory. There's no new elements, no new arrays returned. Yeah, so that's how merge sort is implemented. So let's go ahead and look at merge sort, how merge sort runs. Right, we look at an input that has 8 with 8 numbers, right, in scrambled order. Okay, and the number 1 here and 8 here, they are the indices. Okay, the first element and the 8th element. Okay, so if we call merge sorts on input array A from 1 to 8, according to the algorithm, we'll need to compute the Q. And Q is the midpoint, which is 4, right? So that means following the algorithm, we need to call merge sort again on A, but from 1 to 4. And also merge sort again from 5 to 8. That's 2 recursive calls. And lastly, we need to merge it, okay? So if we just step into the first call, the recursive call here in merge sorts, this recursive call, what it does is to compute a new Q, right? But this Q is in a different scope, it's in this current scope. In the current scope, the new Q is 2. So this 2 is the midpoint between 1 and 4, okay? And it will define another 2 recursive calls, which is from 1 to 2 and from 3 to 4, okay? So let's just go deeper. Go deeper, let's see what we'll find, okay? This deeper call of merge sorts, again, needs to compute a new Q, a new midpoint here, which is 1. 1 is between 1 and 2, right? And there's 2 more of merge sorts recursive calls here. The first one is on 1, 1, and the second call is on 2, 2. But notice that this is already the base call, the bottom case, because when there's only 1 element in the input array, the merge sort will do nothing. It will directly return, okay? Return to the upper level. So they will do nothing. Do nothing, we will go, that means we will return to the previous call, okay? And the previous call is done. We'll go to a different branch, which is to analyze, which is to execute the merge sorts from 3 to 4, okay? And on top of 3 to 4, a new Q is computed as 3, right? And merge on 3, 3 and merge on 4, 4 will also do nothing because they are the base cases, right? And they will return. So after these 2 merge sorts are done, merge will be executed and return to the first merge sorts, to the first recursive call. Okay, I need to use the blue color. Okay, so as you see here, I'm using different colors to indicate different depths of recursive calls. So after this first blue recursive call is done, the second recursive call will be executed in a similar manner as the first recursive call. Okay, and lastly, the merge sort will be executed here in order to get the pyramid built. So in the next slides, we're gonna see how the results are shaped by these different levels, different depths, different recursive calls in different depths. All right, like the first merge between the first element and the second element, where is here, which we see here. Yeah, this is the first merge. The first merge is on A112, okay? That means we are merging the first two elements here. And merging these two elements will give us a sorted subsequence, which is from 2 to 5, which has values 2 and 5. And the second merge is to merge the elements here. It is listed right here, okay? We're merging the third element and the fourth element. And the result is the elements in sorted order, which is 4 and 7, and so on. We'll merge the 5th and 6th, 7th and 8th, okay? And then in the next level of merging, we are actually merging the two subsequences of 2 and 5 and 4 and 7, okay? And the result of merging is 2, 4, 5, 7. And likely, similarly, on the right, the merging will be 1, 2, 3, 6. All right, and then the last level, the top level of merging, if we look at it, it will show us the final merged result, which is in sorted order. Okay. So this pyramid-like type of merging basically shows, given an input, how the elements in the input sequences got compared and merged into sorted subsequences, and shorter subsequences got merged into longer sequences, and finally the complete sequence got merged. Okay.
Professor?
Yes.
So if you were to label like 1, 2, 3, 4, 5, like which order, which one happens, like, do you mind doing that? Just so to help me visualize, like see the order of which one happens first, the steps.
Yeah. I can go through the steps quickly, again, from last step. So if you follow the sequence of the code here, because our first initial call is right here, right? That's our call on the complete sequence, on a whole sequence. And I would rather I will put the 1 here. Okay, this is our first recursive call. And after this recursive call is executed, we will go to here, merge the second recursive call, right? And the second recursive call will be executed further, which is the third recursive call and the fourth recursive call. And the first merge will be here.
Oh, okay. So what happens is like the left side of the array gets sorted first, right?
Yes, yes.
Oh, okay.
Yeah. So the merge sorts will be, the merge here is the first merge occurred, and it will return to the level in the middle. And then the next merge sort recursive call will be this one. So I will put a 5 here. Okay, so this will go into a different branch. Okay, a different branch. and the numbers here would be 6, 7, and this will be the second merge. Okay. Yeah, second merge. Oops. So
okay, got it. Thank you.
yeah. That's basically you build up the left branch, the left pyramid first, and the right pyramid, and then you merge the two subsequences. Yeah.
Okay,
yeah. Any comments? I didn't hear that clearly.
Oh, so when you just have a question. So for the third and fourth call, so basically when you you keep calling merge sort, and then when you get like something like A11 and A1 like A22 like the same numbers, that's how you know you've gone that far, right? That's just like the end of the
Yeah,
if that makes any sense.
This is the end of recursion. Because if you look at the code of merge sorts, when you have P and R's that have the same value, I will go to the previous slide. If you look at the code of the recursion of the merge sorts, if P and R have the same value, the whole body will not be executed.
Okay.
Yeah, so the function, the call will immediately return.
Okay.
Yeah.
Okay, thank you.
Nothing will be done if in a basic case. All right. Yeah, I think it will help you in one of the assignment question. I ask you to draw the plots in a similar way as the slide here. Yeah, but you can work on that by write down all the recursive calls on the paper with different layers, and I think that will better help you understand the procedure. All right, we have a couple more slides to go because we want to not just know how merge sort works, but also want to see that where the advantage is, like how it is a better algorithm than insertion sorts. All right, now, so we basically want to analyze the running time. Okay, so now we have a difficult question. So the merge sorts contains a recursive call to itself. So it's not a kind of regular type of mathematical equations that we can easily analyze. We can easily write it into an analytical mathematical expression, right? So we can basically only describe it by a recurrency equation. Okay, it's not an analytical solution yet. Yeah, the Canvas quiz questions always start one. Yeah, that's basically the convention we will follow. Okay, so for the recurrence equation, we'll basically use it to describe a recursive algorithm. Basically, what it does is to describe the overall running time using the problem size. Okay, and then we try to solve the recurrence equations with mathematical tools. Okay, let's see the example here. Still, we use the notation capital letter T of n to be the running time for the problem of size n. And if the problem is small enough, say it's under some threshold C, the C is a constant, and then we can directly get the solution for those small cases. And let's assume that the solutions can be solved within constant amount of time, written by big theta of 1, okay? And also, let's suppose that we divide the problem into A subproblems, and A is the number of subproblems. And also, each subproblem is 1 over b, the size of the original problem. Okay, so here I use some more general cases where A and B are used. But for merge sort in particular, the A is actually equals 2, right? And the 1 over B actually is 1 over 2, right? So, but the general number A and B means that in a general divide and conquer approach, for different problems, the A and B's can be different values, not necessarily 2 and 1 over 2. Yeah, we will see that later, but it doesn't really matter this time, okay? All right, so let's assume that we've got T of n and A and B all defined. Then we can use the same expression, T of n over B, to denote the time needed to solve one subproblem, okay? And if we take all these A subproblems together, then A times T of n over B is the total amount of time to solve A of them. That makes sense, right? Because T of n is a function that describes a problem given the problem size. Now we know the problem size is n over b, then the time for solving it is T of n over b. And we know that there are A of such problems, then the total time is A times T of n over b. All right, that's the mathematical notations we need to use. So in the case of a complete divide and conquer approach, we also need to consider the time cost to divide and the cost to combine. So we will use another two functions, d of n for the cost to divide and c of n as the cost to combine, okay? And taking that all into consideration, then we can write the final recurrence equation as this, okay? The T of n can be expressed by this equation with two conditions. The first case is the base case, where n is small enough so that we can directly get the solution within constant time. And in other case, if the problem can be divided, then the cost can be calculated by the cost for solving all the subproblems plus the cost of dividing and combining, right? That should include everything we need to spend on solving the original problem. So this thing in total, this set of equations put together, we call it a recurrence equation. All right. So this recurrence equation can be solved, and the question is how. Okay. So we will have a complete chapter dedicated for solving recurrence forms, solving recurrence equations. And today we're going to showcase how that can be done with some intuitive methods. Okay, let's look at how we can solve this recurrence problem. Okay, so basically all divide and conquer algorithms can yield such a form of running times. Well, because whenever we divide, whenever we conquer, we need to consider the cost of divide and conquer and also the cost for solving all the subproblems. All right, now let's look at a simplified analysis for merge sort. Yeah, because in the previous slide, everything is A and B's, and now we need more specific numbers. All right, so in merge sort, we take some simplified assumption. First of all, we assume that the number can be divided by 2, okay? And also the size is always the power of 2. That makes things much easier. And each divide step yields 2 subproblems of exactly n over 2. Okay, that is our simplified assumption. And because the dividing step is just to compute the midpoint, it's just to compute the index q, and q is p plus r divided by 2. That is a primitive computation, which only takes constant amount of time. Okay, and the conquer step, where the recursive calls happens. So in that case, each size of the subproblem, the size of each subproblem is n/2, and we have 2 of such problems. So the total cost for the conquering the subproblems is 2 times t of n/2, right? And in the combine step, we need to use our knowledge from the merge procedure, because merge does the combining step for us. And we already know that the merge has a long for loops involved, and that for loop will takes linear running time. So we can use big theta of n to indicate the cost for combining. All right. So putting that all together, we can write the recurrence for the merge sort as follows. Okay. So in the base case, where the input size is 1, there's only 1 element, then the cost is constant. Okay, something very small. We write it as big theta of 1. In other case, if the number is greater than 1, then we need to consider all these parts together, which is the cost for conquering, the cost for combining, and the cost for dividing. All right. That's a much simpler form than the previous one. Now let's further simplify it, which can be written into this one, because we can ignore the lower order terms, right? We compare it with the linear term. This lower order term is simply insignificant. All right. So that's how we get to the recurrence equations for merge sort. Okay. So there's still a big theta in the equation, right? Big theta in the equation. Then we can get rid of it by assuming that it can be written by some constant c and a simple linear function c times n. And c is just some constants we can imagine, right? All right. So now let's use an intuitive way to understand how t of n looks like, okay, by plotting some trees. Okay, so this is a recurrence. First time we see a recurrence plot here, a recurrence tree plot. Right, so if we look at the equation here, there's 3 parts actually. There's 2 times t of n/2 and a c times n. So if we put c of n in the root node here, and we put the first, if we put 1 t of n/2 on the left branch and the other t of n/2 on the right branch, we basically can draw a tree structure, right? We decompose the equation into 3 parts, and the c of n, the cost for the combining is right here, okay? All right, and that's not the end of the analysis. We can do the further split, because if we substitute n/2 into this equation, if we substitute n/2 into the equation on the left, into the left term, then within the right term, within the right side, it will be n/2 divided by 2, right? Which is n/4. And here it will be c times n/2, right? Which is here, c times n/2, okay? So we further split the 2 nodes will result in the deeper tree or a taller tree, okay? And we can split as many levels as possible until we reach some points that we can no longer split the nodes, okay? Because the node values grows smaller, right? Decrease slower from c times n to c times n/2, c times n/4, until we reach the point where we will reach the constant c. And that is our smallest subproblems of size 1, right? because we further split when we further split a sequence, we can always reach 1, right? So that is a complete tree view of the total running time. So we need to keep in mind that this whole tree indicates the running time for a merge sort algorithm, okay? And then all we need to do is to sum up all the nodes in the tree in order to get the final solution to T of n, okay? So by observing the nodes, we have some good news. So if we look at those levels, the top level, or the root level, it gives us C of n. The level 1, it gives us also C of n. And if we look at all these levels, we will see that they all sum up to C of n, right? Because if you look at the last level, the bottom level, an input that has n numbers, then the cost will be C times n, right? Because each number corresponds to 1C, right? So all we need to do next is to sum up all these C of n's, right? So now we need to use another piece of information. We know that each level sum up to C of n, to C times n. So we need to know the number of levels or the depths of the tree, right? And that is also easy to analyze. So because according to our intuitive observation, we know that for a particular level I, the number in the node is C times n divided by 2 to the power of I, okay? So this I can be 0. So for the level 0 here, 2 to the power of 0 is 1. And the C times n divided by 1 is just Cn. It's just a Cn here, okay? And for this level 1, the number is C times n divided by 2 to the power of 1. And for level 2, it's C times n divided by 2 to the power of 2, right? So that is the truth we can observe. So for level I, we can have the number in the nodes as follows. And another knowledge is that when the tree hits the bottom level, this number will hit C, right? The number will hit C. So we can let C times n divided by 2 to the power I equals C, and we can eliminate C, and that will give us a solution to I, which is the logarithm of n. And this logarithm has a base 2, okay? And that is how we know that for this bottom level, the level index should be logarithm of n, okay? And since the index starts from 0 here, then we will have logarithm of n plus 1 levels in total, okay? So for this step of analysis, I think you can spend more time after the course, after this lecture is done. But with this information, it's easy to find that the total running time is the logarithm of n times C of n, which give us this form. So the number in the nodes is this number. So you can think of it as a tree node here. It's a tree structure here. So the number in the node is a number in the circle here. Okay. All right. So we take the same principle by ignoring the lower order terms. By ignoring the linear term, then we can describe the running time for the merge sort to be big theta of n times logarithm of n. Okay, that is how we obtain the solutions to the running time of merge sorts. Okay, and we will see that. Let's finish this slide. Compare with insertion sorts. The average case is a quadratic function. And to come up to that conclusion, we analyze the worst case, right? And for merge sort here, we didn't place any assumption on the inputs. We didn't assume whether the input is sorted or reverse sorted, but given the arbitrary inputs, we can basically have a pretty stable analysis, which is big theta of n times logarithm of n, which is independent of the inputs, okay? And this type of function, n times the logarithm of n, grows much slower than a quadratic function, okay? Because if you look at the shape of a logarithm function, it'll be like this. It'll be grows really slowly as n grows, as n increases, okay? And that is basically why merge sorts is a better sorting algorithm than insertion sorts in terms of running time, okay? And we will see a lot of examples like this where the logarithm terms are involved, which brings significant improvement to the running time of algorithms, okay? And that's pretty much of it for the getting started lecture. So I think there's some slides in the lecture today and in the previous lecture on Tuesday that I didn't cover, which is about analyzing the correctness of an algorithm. I think if I have time next week, or we can I can cover that parts a little bit. And also, there's some convention for the pseudocode part that I didn't particularly mention, but we can do that in the next lecture to cover that up. Yeah, I will release the questions for the first week today, and you will soon see the type of questions. And I can also release an expected and release date for each assignments in the future. Yeah, that's something I can publish to Canvas. Okay, so basically the other assignment questions are short answering and code completion. Yeah, you will see a bulk of code and there's some missing lines. And in order to complete the function of the algorithm, you need to write the correct code. All right, and are there any questions? Okay, thank you guys. Thank you for coming, and I will stop recording and